All right, let's dive in. Today, we are getting our hands dirty with a piece of tech that truly connects our code to the real world, the Arduino Uno. Now, if you're in computer science, you're used to code that just lives in the digital realm, right? On a screen. But what happens when you want that code to, actually do something, to move something, to sense something? That's what this is all about. We're going to peel back all the layers from the silicone brain of this thing, the ATmega328P, all the way up to the code that makes it tick.
So here's the plan. First, we'll look at the brain of the operation, the ATmega328P chip. Then, we'll get into the language, the essential commands you need to know. We'll even peek under the hood at how the CPU does math. After that, a quick look at the Arduino IDE, which is where you'll be working. And we'll wrap up with some really cool stuff, timers and PWM, which is how you get super precise control.
Okay, first things first, let's talk about the hardware. All that amazing code you're going to write, it's just a set of instructions for this little piece of silicon. So if you really want to write good, efficient code, you've got to understand the machine it's running on. And that all starts with the architecture of the ATmega328P.
And here it is. This little guy is the ATmega328P. It's the absolute heart and soul of the Arduino Uno. It's what we call a system on a chip, which is just a fancy way of saying it's got everything it needs. The CPU, the memory, the I/O stuff, all baked into one tiny package. It's basically a miniature, purpose-built computer made specifically to talk to the outside world. So, what's actually packed inside? Okay, so this chip uses something called a Harvard architecture. Now, you're probably used to the von Neumann architecture from your desktop PC, where code and data have to share the same road, the same bus. Well, Harvard architecture is different. It gives code and data their own separate highways. Why does that matter? It means the CPU can grab the next instruction while it's working with data. It's a massive performance boost, especially for a compact little controller like this one.
So at its core, we've got an 8-bit RISC-based CPU. But a CPU is kind of useless without memory, right? And this chip actually has 3 different kinds. Think of it this way. First, you've got 32 kilobytes of flash memory. This is like the chip's hard drive. It's where your program, your sketch, is stored permanently. Power it off, power it back on, your code is still there. Then you have 2 kilobytes of SRAM. This is the RAM, the scratch pad. It's super fast memory for variables and all the stuff your code is actively working on. But it's volatile, meaning when the power goes out, poof, it's all gone. And lastly, there's 1 kilobyte of EEPROM. This is like a tiny, built-in notepad for saving small bits of data you don't want to forget, even with no power, like maybe a high score or a user preference.
So how does this chip actually talk to anything? Through these pins. They're its connection to the outside world. You've got your digital pin 0 and 1, that's for serial communication, basically how it talks to your computer. Pins 2 and 3 are special, they're for external interrupts, which lets your code react instantly to something happening. See those little squiggly lines next to some pin numbers? Those are your PWM pins. We'll talk all about that magic later. And finally, you have the analog input pins, which are perfect for reading sensors that give you a whole range of values, not just on or off.
Okay, so the hardware is cool and all, but how do we actually tell it what to do? Well, that's where the Arduino language comes in. These essential functions are your toolkit. They're how you're going to command those pins and make your projects actually do stuff. This is the bridge from your keyboard to the real world.
The basic digital input/output. It's really a simple 3-step dance. First, in your setup code, you use pin mode to tell a pin what its job is. Is it listening for a signal? That's input. Is it sending a signal out? That's output. Then, once your main loop is running, you'll use digital read to check if an input pin is high or low. Or you'll use digital write to command an output pin to be high, which is 5 volts, or low, which is 0 volts. That's it. Set it up, then read or write.
Let's make this real. Look at this circuit. We've got a motion sensor hooked up to one of our input pins and a little LED on an output pin. So, what's the code doing? Well, first, you'd use pin mode to tell the Arduino, hey, this pin is for listening to the sensor and this other pin is for controlling the LED. Easy enough. Then, inside your main loop, it's constantly asking, what's the sensor saying? It uses digital read for that. If it reads high, bam, motion detected, it immediately uses digital write to send 5 volts to the LED, turning it on. It really is that simple. Read, decide, act. But the world isn't always just on or off. Sometimes you need shades of gray. What about a dimmer switch or a volume knob? That's where analog read is your best friend. The ATmega328P has a built-in analog-to-digital converter, an ADC. and it's a 10-bit converter. All that means is it can see 1,024 different steps. So analog read looks at an analog pin, sees a voltage anywhere between 0 and 5 volts, and turns it into a number from 0 to 1023. This is absolutely critical for reading all kinds of sensors, like light sensors or temperature sensors that give you a range of values.
Okay, let's talk about time. In almost every project, you'll need to control timing. The simplest way is the delay function. You tell it to wait for, say, 1,000 milliseconds, and it just stops. The whole program freezes for 1 second. This is called blocking code, and it's like telling your program to hold its breath. It can't do anything else while it's waiting. The much smarter way to do things is with millis. This function is like a stopwatch that started the moment your Arduino turned on. Instead of stopping everything, you just check the clock. You can say, has it been a second since I last blinked this LED? This is non-blocking, and it's the secret to making your Arduino do multiple things at once.
All right, time to go a little deeper. This is for the real computer science folks out there. You've typed a million math equations in your code, right? But have you ever stopped to think about what the CPU is actually doing on a hardware level when you type something simple like x equals y times 7? We're going to pop the hood and look at the actual binary magic happening inside the arithmetic logic unit. So this is Booth's multiplication algorithm. Now, a simple way to multiply would be just to add a number to itself over and over, but man, is that slow. Booth's algorithm is a way more clever and efficient method for multiplying binary numbers, especially signed ones. Basically, instead of just adding, it looks at the bits in pairs and makes a smart decision. Should I add, subtract, or just do nothing? Then it does a quick shift. It's a really elegant hardware trick that makes multiplication happen way faster.
Okay, let's actually walk through an example. 7 times 3. So 7 is our multiplicand, M, and 3 is our multiplier, Q. That A register, the accumulator, starts at 0. On the first pass, the algorithm looks at the last 2 bits of Q, which are 1, 1. The rule for 1, 1 is do nothing, just shift. Okay, next cycle the bits are 0, 1. The rule for 0, 1 is add M to A and then shift. We just keep repeating this process for each bit, and by the end you look at the A and Q registers combined, and what do you have? The binary representation of 21. It's seriously cool when you see how the hardware pulls it off.
Okay, we've got the hardware. We know the basic commands, but where do we actually, type the code? That would be the Arduino IDE. Think of it as your digital workshop for writing, checking, and sending your code to the board.
The IDE is meant to be super straightforward. You write your code, which they call a sketch, right here in the main window. It's got nice features like syntax highlighting that helps you spot typos. Now, before you upload, you have to do 2 crucial things. Go to the Tools menu, pick your board, in our case, the Arduino Uno, and then pick the right COM port so it knows where to send the code. After that, you just smash that upload button. The IDE does all the heavy lifting, compiling your C++ code into machine code the chip understands and zapping it over the USB right into the chip's flash memory. You can watch it all happen down in that little output window.
All right, for our last section, we're going to level up. We're going to talk about something that really shows off what this hardware can do: mastering time. We're going to look at the chip's internal timers to create super precise signals and even fake an analog output using a really cool technique called pulse width modulation. So what on earth is pulse width modulation, or PWM? The idea is actually genius. A digital pin can only be on or off, right? 5 volts or 0 volts. It can't output, say, 2.5 volts. But what if you could switch it between on and off really, really fast? Imagine you're flicking a light switch on and off hundreds of times a second. Your eye wouldn't see the flickering. It would just look like the light is dimmed. That's PWM. By changing how long the on time is compared to the off time, you can control the perceived brightness, or, in our case, the average voltage.
The magic word here is duty cycle. It's just the percentage of time the signal is high or on. So a duty cycle of 0%, the pin is always off, average voltage 0. A duty cycle of 100%, the pin is always on, average voltage 5 volts. So what about a 50% duty cycle? Well, it's on for half the time and off for the other half. The average voltage your circuit sees is, you guessed it, 2.5 volts.
And the math behind it is super simple. The average voltage you get is just the duty cycle percentage times your max voltage, which for the Uno is 5 volts. So yeah, if you need 1 volt, you set a 20% duty cycle. Need 3.75 volts? That's a 75% duty cycle. It's completely predictable. Now, to make these super fast, super precise pulses, the chip doesn't use software delays. It has dedicated hardware timers. There are 3 of them.
Timer 0 and Timer 2 are 8-bit, meaning they count from 0 to 255. They're great for most things. But the real powerhouse is Timer 1. It's a 16-bit timer, so it can count all the way up to 65,535. That higher number means you get much, much finer control over your timing and PWM signals. And what's this prescaler thing? Think of it like a gear on a bike. It lets you slow down the clock speed that the timer uses so you can measure much longer periods of time without the counter overflowing.
So, what's a perfect real-world example of this? Controlling a servo motor. Servos are interesting. They don't care about the average voltage. They care about the width of the pulse you send them. For most standard servos, a pulse that's 1 millisecond long tells it to go all the way to one side. A 2 millisecond pulse sends it to the other extreme, and a 1.5 millisecond pulse puts it right in the middle. You have to send these pulses over and over, and those hardware timers we just talked about, they are perfect for generating these signals with pinpoint accuracy to control a servo's angle.
So let's just wrap this all up. The next time you sit down and type a simple line of code like analog write LED pin 128, just pause for a second. Think about everything that's actually happening under the hood. That one command kicks off this incredible chain reaction. It gets compiled into machine code for the CPU, which then tells a dedicated hardware timer to start spitting out a perfectly timed series of on-off pulses, all just to make an LED glow at half brightness. It's this beautiful, complex dance between the software you write and the silicon it runs on. And that's the question to leave you with. When you write that one line of code, what complex dance are you really conducting?